in session 1.3, I want to introduce you a sinusoidal wave. And everybody knows that a sinusoidal function is quite important in a linear analysis because in the linear system, if you know the solution of a sinusoidal function, then you can use the superposition to synthesize the solution for an arbitrary signal. So now I want to remind you a sinusoidal wave. This is just a function of time, and this is something we often see on an oscilloscope. For example, if you are testing an electronic circuit and then you pick up the voltage signal into an oscilloscope, then you see this oscillating signal over time. And when you describe this signal, you use some amplitude, and then you use a cosine or sine function to describe it. So in this function, you have an amplitude psi 0, and you have a starting phase theta 0 here. If this point match to this point, then you have cosine 0. If you match this 0 point to this beginning point, then you have a sine function. At the same time, there's a variable to describe how fast this signal will oscillate in time. We call this omega, which is the angular frequency of this sinusoidal signal as a function of time. Well, the same mathematical formula can be used to describe a sinusoidal function in space. You can see that this is the sinusoidal function with the amplitude again. Here, the maximum point of this oscillation is the label as psi 0. And now the amplitude changed over distance z. So you plot this psi of z as a function of z, and you see oscillatory behavior of this cosine function. Again, you have a starting phase theta 0 here, and also you have a term describing how fast the oscillation of this sinusoidal function is. Here we label is k, which is 2 pi over the wavelength of this periodic function. So this is a sinusoidal signal in space. Now we want to borrow this sinusoidal function to describe a wave propagating in space. But we know that a wave propagating in space over time is described by this wave function Bo-Hanshu of this form. So let's just borrow this sinusoidal function as a function of time and change the variable t to t minus z over u. Suppose this wave propagate along z direction. So with this substitution, you end up having this sinusoidal function as a wave function which describe a sinusoidal wave propagating along z direction. So if I just multiply this omega with t, then apparently this omega is the angular frequency of the wave. And this omega multiplied with u, which tells you the periodicity of the sinusoidal function along z direction. And from last page, we say this periodicity is described by this k variable, which is 2 pi over the spatial periodicity, or 2 pi over the wavelength. And let's try to plot this like this. This is the density plot of this cosine function. You can see the amplitude varies along z direction with some spatial periods. So if I just cut this density plot and plot the psi as a function of time or position z, you will see such an oscillatory curve on this plot. And you see peak and also trough denoting the amplitude of this sinusoidal function. And the whole field pattern, the whole amplitude pattern will move in space over time. And the spatial period of this pattern is called the wavelength of this wave. But if you try to describe it as a function of time, then we denote as t, which is the inverse of the frequency of this wave function. So this cosine function describes a single frequency sinusoidal wave propagating along z direction, and the wavefront is coincide with the a plane with the perpendicular direction along z direction. So now that we have a sinusoidal function, we call this the harmonic wave. It's described by time harmonic in this function. And if we just pull out this exponential j omega t, then we have phasor, and we have discussed this before in lecture 2 of the 电磁学1. And this time dependence exponential j omega t is always there when we do analysis. So in fact, we can just factor out this exponential j omega t during our calculation. So to simplify the calculation, let's just try to do this phasor calculation. And then once we have the solution of this phasor notation, then we put this exponential j omega t back to the expression to construct the full expression. So let's try to convert this wave equation into equation described by the phasor. And in lecture 2 of EM1, we know how to do it. For this variable psi, you basically just replace this with the psi with the head, which is the phasor of this real function. And when you have a differentiation of the variable with respect to time, then you drop out this j omega. If you differentiate it twice, then you drop j omega square into this expression. Then finally, the u is equal to k over omega, which is the given from the last page. In fact, this is 1 over u is k over omega. If this u, then we have omega over k. So you just replace this 1 over u square with the k square over omega square. Then you can construct this Helmholtz equation. Now in this equation, there's no time variable. You take out this time variable, and then you solve the phasor from this Helmholtz equation. Once you have the solution from this Helmholtz equation, then you can put this exponential j omega t back and take real part of the multiplication of these two terms. Then you have the real solution. And this will simplify the calculation, because now if you start from this wave equation, you have to deal with two variables, time and coordinate. But if you start from this equation, you'll be dealing with just one variable, which is the coordinate. So this will simplify the calculation. And finally, you can convert this expression back to a sinusoidal wave like this. And this will complete the analysis. 所以呢，在这一章里头，这个小节我们介绍了所谓的弦波 sinusoidal wave。因为在一个线性系统里头，你若有一个弦波的解的话，那你可以把很多的弦波的解呢，把它加起来，来这个组合成一个特定讯号的一个解。那这是线性系统里头常做的一个这个分析，我们叫做傅里叶分析。所以呢，在这一个小节里头，我们介绍了一个harmonic wave 的这个 sinusoidal wave given by this expression。那在这个里头呢，这个 cosine 里头，这个 omega 是这个波的角频率 angular frequency， 那是等于2π乘上这个波的频率。那 k 呢叫做 wave number， 这个 wave number 呢是2π除以这个波的波长。那这个 theta 0呢就是这个波的一个起始的相位。那这个 cosine 的这个式子可以用phasor的方式来表示，也就是把这个时间的部分呢把它抽离出来，然后乘上一个phasor，再取它的实数，然后在分析的时候呢你可以把这个 exponential j omega t 整个抽离出来，所以呢这个 wave equation 可以变成 Helmholtz equation。在这个 Helmholtz equation 里头呢，只有这个位置的变数，而没有时间的变数，所以分析起来就容易得多。 一旦你有这个解，从这个Helmholtz equation 里头把这个跟位置相关的这个解出来之后，你可以再乘上 exponential j omega t 取它的实数，然后呢回复到原来的这个解。所以这是弦波的一个介绍，然后呢也告诉你说一旦你有这个 harmonic wave 的话，分析起来会容易得多一方面你可以把时间跟这个空间的变数把它分离，那另一方面的话呢，在一个线性系统里头，你如果知道一个弦波的一个这个特定频率的解的话，你可以用傅里叶分析把一些这个相关的解把它加起来变成完整的一个解。那这个是第3小节的一个介绍，谢谢。